In 2017, a mysterious traveler zipped through our solar system at speeds so staggering that astronomers around the world were left in awe. This object was unlike anything we had ever observed before. Scientists quickly realized they were witnessing the first confirmed interstellar visitor, an object that had originated far beyond our solar neighborhood. Named Oumuamua, meaning scout or first messenger in Hawaiian, this enigmatic visitor raised as many questions as it answered. By the time astronomers detected it, it was already streaking out of our solar system, leaving only fleeting observations in its wake. With the scant data available, its true nature remains elusive, and its origins even more mysterious. Yet, what truly sets Oumuamua apart from every other object we have studied is not simply the fact that it came from another star. It is the way it moved. Its motion defied conventional physics, so much so that some scientists have suggested that the only plausible explanation might be alien technology. What exactly is Oumuamua? What did it do that so startled astronomers? And perhaps most importantly, are there countless other visitors like it, slipping through the cosmos, unnoticed? To understand just how extraordinary Oumuamua is, we need to consider the broader context of interstellar objects. Astronomers estimate that the galaxy is teeming with these wanderers. Some researchers predict that up to 10,000 interstellar objects pass within Neptune's orbit every single day. That number seems astronomical, almost impossible to grasp, but it's based on a careful understanding of our solar system's structure. Beyond the familiar planets lies the Kuiper Belt, a vast, icy region extending beyond Neptune. And further out still, almost unimaginably distant, is the Oort cloud, a spherical shell of trillions of icy bodies gravitationally bound to the Sun. Many of the comets we see passing through the inner solar system originate from this Oort cloud, traveling along highly elliptical orbits that may take them tens or even hundreds of thousands of years to complete. However, the majority of these icy travelers would never venture close enough to the Sun were it not for gravitational nudges from massive third bodies. Often, these perturbations come from other stars, as the solar system itself is not static. It is in constant motion, orbiting the center of the Milky Way at incredible speeds. As our system journeys through the galaxy, it occasionally passes near other stars, whose gravity can deflect comets, sending them tumbling inward or slingshotting them into interstellar space. This dynamic process means that over millions of years, countless objects are ejected from their home systems, drifting forever between the stars. Likewise, our Sun may occasionally capture an interstellar visitor. But what does this mean for objects like Oumuamua? The implications are profound. It tells us that the universe is not a static place, and that interstellar wanderers may pass through our solar system far more frequently than we ever imagined. The question isn't whether such objects exist, they do, but rather whether we are capable of detecting them, given their often tiny size and extraordinary speeds. And Oumuamua gave us a dramatic glimpse of just how elusive these visitors can be. Discovered on October 19, 2017 by the Pan-STARRS telescope at the Haleakala Observatory in Hawaii, Oumuamua initially appeared to be a comet and was classified as C/2017 U1. Yet upon closer inspection, astronomers saw no evidence of a cometary coma, the cloud of gas and dust that typically surrounds a comet's nucleus. It was then reclassified as an asteroid, receiving the designation A/2017 U1, marking the first time in history that an object had required such a reclassification. The observations revealed that Oumuamua was following a hyperbolic trajectory. Unlike planets, comets, and asteroids bound by the Sun's gravity, a hyperbolic path indicates that an object is moving fast enough to escape the solar system entirely. In other words, Oumuamua was an interstellar traveler, passing through our neighborhood for a brief, fleeting moment before continuing its journey into the void. This realization led the International Astronomical Union to create a new classification for such objects, the I designation for interstellar, cementing Oumuamua's status as one I/2017 U1. Early measurements suggested that this object was small, somewhere between 100 and 1,000 meters in length, and possibly elongated in shape, reminiscent of a cigar or perhaps even a flattened disc. Its unusual brightness variation, pulsating every 7 hours, indicated that it was tumbling through space rather than rotating smoothly along a single axis. This tumbling motion, combined with its shape, added to the growing mystery surrounding it. How did such a peculiar object get ejected from its home system? Was it the result of a catastrophic collision, or was there another explanation altogether? While shape and size were intriguing, what truly baffled astronomers was Oumuamua's acceleration. When it passed closest to the Sun on September 9, 2017, it was traveling at an incredible 87 kilometers per second. Normally, we would expect an object to slow down slightly as it moves away from the Sun, pulled by its gravity. Yet, Oumuamua defied this expectation. It accelerated instead. Rob Werrick, the astronomer credited with its discovery, noted that its motion could not be explained using any conventional model of a solar system asteroid or comet. Scientists quickly began searching for a plausible explanation. Could solar radiation pressure, the gentle push of sunlight, be responsible? This phenomenon can indeed accelerate small objects in space, but the force required to account for Oumuamua's behavior seemed implausible for an object of its size and mass, unless it was extraordinarily thin, like a sheet of paper stretched hundreds of meters long. Another possibility was cometary outgassing. Comets produce jets of gas and dust as ices vaporize near the Sun, which can act like thrusters and alter their trajectories. Yet no such outgassing was detected from Oumuamua. Even the Spitzer Space Telescope spent 30 hours attempting to detect infrared emissions that would indicate sublimating material, but none was found. Moreover, its reflectivity was unusually high, 10 times brighter than a typical comet, suggesting that it might be composed of a more metallic material. The absence of detectable outgassing and the anomalous acceleration led some scientists to consider a more radical explanation. Harvard astrophysicist Avi Loeb proposed that Oumuamua could be an artificial construct, a light sail designed to harness the pressure of starlight for propulsion. In 2018, Loeb argued that the only way solar radiation could account for the observed acceleration was if the object were extremely thin, potentially just a fraction of a millimeter thick, an engineering marvel beyond natural processes. This hypothesis ignited intense debate, with many in the scientific community rejecting the idea as improbable. Other researchers explored alternative natural explanations. Postdoctoral researcher Darryl Seligman suggested that Oumuamua might be composed largely of molecular hydrogen, forming a hydrogen iceberg that sublimated invisibly as it approached the Sun. This dark comet hypothesis could explain both the acceleration and the lack of visible outgassing. However, Loeb countered that such a hydrogen iceberg would not survive the long journey through interstellar space, arguing that interstellar radiation would have evaporated it long before reaching our solar system. Undeterred, Seligman and colleague Jennifer Bergner proposed a refinement of the dark comet idea. Laboratory experiments suggested that hydrogen could be trapped within water ice under extreme cold and released later when warmed, a mechanism that might naturally occur in space aided by cosmic radiation. This explanation accounted for the acceleration without the need for visible outgassing, opening the possibility that Oumuamua represents an entirely new class of object, a dark comet, invisible in many wavelengths yet capable of propelling itself through space. The story doesn't end there. Intriguingly, Seligman and colleagues identified 6 other small objects within our solar system that exhibit similar unexplained accelerations, despite lacking visible outgassing. These near-Earth objects, some as small as 3 meters across, appear to experience minor, non-gravitational accelerations. One of these, 1998 KY-26, is set to be visited by the Japanese Hayabusa 2 probe by 2031. Although it's far too small to be a light sail, studying these accelerating objects may provide insight into the physics behind Oumuamua's motion and test the dark comet hypothesis. Yet, Even if Oumuamua is not a piece of alien technology, it remains an object of immense scientific interest. Its journey through our solar system represents a unique opportunity to study material from another star system. Tracing its trajectory backwards suggests it originated from the direction of Vega in the Lyra constellation, with several candidate home stars identified up to 81 light-years away. Today, it lies over 6 billion kilometers from Earth, moving toward the Pegasus constellation at 26 kilometers per second, far beyond the reach of our telescopes for detailed study. Because of its fleeting visit, scientists have considered the ambitious idea of sending a probe to intercept Oumuamua. The challenge is formidable. The object is moving far faster than any spacecraft we've launched. Reaching it requires incredible speeds, precise navigation, and advanced propulsion techniques. 2 mission trajectories proposed by Project Lyra illustrate potential approaches. One involves a gravity-assisted slingshot around Jupiter, followed by a solar Oberth maneuver near the Sun to achieve the necessary velocity. The second trajectory employs flybys of Venus and Earth, culminating in a gravity boost from Jupiter to launch a probe toward the interstellar object. Both approaches face technical and logistical hurdles, including extreme thermal protection, precise orbital timing, and fuel limitations. Looking ahead, new observational tools promise to improve our ability to detect interstellar objects before they pass too far from Earth. The Vera C. Rubin Observatory, launching its legacy survey of space and time in late 2025, could identify objects like Oumuamua months in advance, potentially capturing dozens of interstellar visitors each year. Similarly, ESA's Comet Interceptor mission, set to launch in 2029, will wait in space for an incoming interstellar object and perform a close flyby to map its structure and composition, offering unprecedented insights into these cosmic nomads. Even with these technological advancements, the fundamental questions raised by Oumuamua remain unanswered. Is it a dark comet, a fragment of an alien civilization, or something entirely different that we have yet to imagine? Only direct observation, careful measurement, and rigorous analysis can provide answers. The story of Oumuamua reminds us of the profound mystery of the universe, highlighting how much we have yet to learn about the objects that silently traverse the galaxy, passing through our solar system unnoticed for millennia. From its discovery to ongoing debates and ambitious mission proposals, Oumuamua challenges our understanding of physics, astronomy, and the very possibilities of life beyond Earth. Whether a natural phenomenon or evidence of intelligent design, it has expanded our perspective on the cosmos and inspired a new generation of scientific inquiry. As we prepare for future interstellar visitors, we can only wonder what secrets the next Oumuamua might hold, and how it will reshape our understanding of the universe once again. The study of these interstellar travelers is more than an academic exercise. It's a testament to human curiosity, ingenuity, and the relentless drive to explore the unknown. Each passing object offers a glimpse of distant worlds, the material from which stars and planets are formed, and perhaps even the faint traces of civilizations beyond our solar system. And while Oumuamua has long since disappeared into the void, it remains a symbol of the mysteries that await us, inviting us to keep looking, keep wondering, and keep reaching for the stars. Whether through high-tech missions, novel observational techniques, or the next serendipitous discovery, our understanding of interstellar objects is poised to grow exponentially. With each new object, we refine our models, challenge our assumptions, and deepen our appreciation of the galaxy's complexity. And in that pursuit, whether Oumuamua turns out to be an exotic comet, a natural oddity, or a messenger from beyond, it has already changed the way we see our place in the cosmos. Ultimately, the tale of Oumuamua is far from over. Its passage may be brief, but its impact on science, imagination, and the endless quest for knowledge will endure for decades to come. We may not yet know its full story, but the questions it poses, the what-ifs and the why-nots, are exactly the fuel that drives humanity to explore ever further, to probe ever deeper, and to never settle for the boundaries of what we think we know. In the vast, silent expanse of interstellar space, objects like Oumuamua are cosmic messengers. They remind us that the universe is alive with motion, full of strange phenomena waiting to be discovered, and that sometimes even a tiny object passing through our solar system can ignite a cascade of wonder, debate, and exploration that spans the globe. Whether a dark comet, a fragment of an alien civilization, or something entirely unexpected, Oumuamua's legacy will persist, guiding scientists, dreamers, and explorers alike as we continue to chart the mysteries of our galaxy, and perhaps one day, the universe beyond.